Okay. Good afternoon to one and all. I think I am visible and audible to all. Am I? Are you able to see me? Yes. Yeah, good afternoon. Good afternoon. Okay. Let's start with the today's session. Thank you so much for your response. So today we are going to start the new chapter. Okay. So the name of the chapter is atomic structure. Yeah. The topics that we are going to cover in this lesson are Bohr's atomic model, de Broglie equation, Heisenberg's uncertainty principle, photoelectric effect, quantum numbers, and the rules for filling up of electrons. Okay. So we will try to cover as much as we can, and since we have only half an hour more in front of us, we will try to cover this, and the remaining part we will discuss in the next class. Okay. So coming to the Bohr's atomic model, so this model was proposed by Niels Bohr in 1930. Okay, and it is applicable only for single electron species like hydrogen. In hydrogen, we have only one electron, right? And in helium plus also, atomic number for helium is 2, and it has lost one electron, so the number of electrons here also 1. And in case of lithium 2 plus also, if you see, the atomic number of lithium is 2, and lithium has lost 2 electrons. So atomic number of lithium is 3, and it has lost 2 electrons. So the remaining number of electrons present in it will be 1. And for hydrogen also, the atomic number is 1, number of electron is 1. So this model is applicable to one electron species, single electron species like this. Okay, and it is based on the particle nature of electron. Okay, an electron can have both wave and particle nature, but here Bohr's atomic model talks about the particle nature of electron. Okay, so these are the very important introductory points we should know about the Bohr's atomic model. With this, let's move on to the postulates of Bohr's atomic model. Okay, so we have few postulates, some 5 to 6 postulates we have here. All the postulates are very, very important. Okay, very important for your class 11 exams as well as for your NEET and JEE exams. So the first postulate states that an atom consists of small, heavy, and positively charged nucleus in the center, and the electrons revolve around it in a circular orbit. So we have an atom, and that atom has nucleus at the center, and the electrons are revolving around that nucleus in a circular orbit. This was the first postulate. Okay, circular orbit. This is very important. You have to keep this in mind. Then coming to the next point, the attraction or the attractive force between the nucleus and the electron is equal to the centrifugal force. So electron is negatively charged and nucleus is positively charged. So plus and minus, what they will do? They will try to attract each other. So this is the attractive force between the nucleus and the electron. Okay. And also there is one more force acting, that is centrifugal force. So what is centrifugal force? It will go like this. If electron is here, it will act like this. Okay. If the electron is here, if it will act like this. So the centrifugal force will try to, they will act away from the nucleus. So electron, if it is coming towards the nucleus, it is attractive force. If the electron is trying to go away from the nucleus, then that force is called a centrifugal force, which is acting on that electron. Okay. So both the force will be equal. So if electron is placed here, and if one force is bringing this electron here, and if another force is bringing this here, taking this electron there, and what will happen? The electron will not move to the left or right. It will stay in the center part itself, right? So that is the orbit. That is the circular orbit in which the electron is located. So it is neither coming this side nor going that side. It is staying in its place. Got it? So both the forces are equal. So it is revolving in a circular orbit because of this. Then coming to the third postulate, electrons can revolve only in those orbits in which the angular momentum of electron is the integral multiple of h by 2 pi. So MVR is the angular momentum. Mass into velocity into radius of that electron is the angular momentum. That is equal to the integral multiple. Integral means integer, n. Integral multiple of h by 2 pi. And this h by 2 pi is equal to h cross. So instead of this h by 2 pi, we can substitute h cross, and from that we are getting MVR is equal to N h cross, which is a very important formula. N is the positive integer number and h is the Planck's constant we all know, and pi is the constant, that is 22 by 7. Okay. And N can be 1, 2, 3 or 4. So we can have h by 2 pi, 2h by 2 pi, 3h by 2 pi. So like that it goes on. Okay, the fractional values are not included. So 1.5, 0.5, 1.2. So this kind of multiple of h by 2 pi is not allowed for this system. Got it? So it can have only the integral value. It cannot have the fractional values. Got it? Then coming to the fourth postulate, the orbits in which the electron can revolve. So it is revolving in that circular orbit. No? So those orbits are called a stationary orbit. Means it will not move. It will remain in a stationary place. Okay. Because in these orbits, energy of the electron is always constant. Energy of the electron is always constant. For example, you can take this diagram. So we have orbit number 1, orbit number 2, orbit number 3, orbit number 4, right? So if this is the first orbit, that is the K shell, there will be some energy associated with that. Okay, the electrons which is present inside that particular orbit, so those electrons will have the same value of that energy, because energy of the electron is always constant in that single system. Okay, so and likewise it follows for the second orbit, third orbit, fourth orbit. So all these orbits are stationary, they will not move, and that's why the energy of the electron is constant there. Okay, and each stationary orbit is associated with definite amount of energy, and that's what we have discussed. And these orbits are also called as energy levels. Okay, and are numbered as 1, 2, 3, 4, 5 or KL, MN from the nucleus. Okay, we all know this, right? K shell, M shell, N shell, and N shell. So K shell is denoted by number 1, L by 2, M by 3, and N by 4. So it goes on. Clear? And then coming to the last postulate of this Bohr's atomic model, it is the emission or absorption of energy in the form of photon can only occur when electron jumps from one stationary state to another stationary state. So you see here, we have N is equal to 1, 2, 3, 4, 5. Okay. And there is one electron, red color electron present in N is equal to 1. Okay. And if this electron absorbs some energy, it is absorbing that energy and it is going to the N is equal to 3 level state. Okay, that is called as energy of absorption. Or if an electron is present in N is equal to 5, and if it tries to come to N is equal to 2, then what does it do? It emits the energy which it is having. That is the emission of energy. So it is absorbing the energy as well as it is emitting the energy. Those both things are happening in the form of photon. Okay, when electron jumps, it is absorbing, and when electron comes to the lower energy state, it is emitting the energy. So the change in this energy value is measured using this formula: higher energy state minus lower energy state. Final energy N2 minus N. Okay, energy is absorbed when electron jumps from inner orbit to outer orbit, and it is emitted when electron moves from outer orbit to inner orbit. So always the N2 will be greater than N1, whether emission or absorption of energy will occur. Okay, so suppose if this is N is equal to 1, this is N is equal to 2, it is 3, it is 4, it is 5. If an electron present in 5, if it tries to come to the third energy level, it is emission. If something, if 1 from 3 it is going or 4 it is going, it is absorption. Clear for all? So all the 6 postulates of Bohr's theory, is it okay for all? Any doubt from this? The main thing is, it is applicable only for one electron species, and it keep in mind the particle nature of electron. So these two are very important, and all the 6 postulates. Electron is moving in a stationary orbit, and it is having this kind of energy of absorption and emission, and it is the angular momentum is the integral multiple of h by 2 pi. NH by 2 pi. So all the things are very important. Attractive force is equal to the centrifugal force. Okay. So all these points you have to keep it. Is it okay? Shall we move on to the applications of Bohr's atomic model? Is the postulates clear? Okay, okay. Thank you, Aisha. So we'll go for applications. So the applications of Bohr's atomic model are we can able to find out the radius of the various orbits on the shell. So from Bohr's atomic model, firstly we can find out the radius of the shell using this formula, which is very, very important. 0.529 into n square by z. N square is the number of the orbit and z is the atomic number. Okay, n square by z angstrom. And the next we can find out the velocity of an electron also by using this formula. 2.188 into 10 power 6 z by n, where z is the atomic number and n is the number of the orbit again. And the energy of an electron can also be calculated by minus 13.6 into z square by n square. In terms of electron volt per atom, you can use this formula to find out the energy. And if we want to find out the delta E, that is energy difference, if we want to find out, we can do final energy level minus initial energy level by putting minus 13.6 into Z square. Z is the atomic number again, and 1 by N2 square minus 1 by N1 square. N2 is the final state and N1 is the initial state. Okay. So these are the formulas you have to note down, and these will be very helpful in solving the numerical part from this lesson. Is it okay? Clear? Did you all note it? Write down this and keep it in your notebook. Shall I move on to the next slide? So I think Bohr's atomic model, its postulates and the applications are clear to all of you. Am I right? Shall I go on with the next topic? We will do one more topic. Students, shall I move on to the next topic? Say yes or no? Okay. So the next is de Broglie equation. So according to de Broglie, the wavelength, that is the lambda of an electron, is inversely proportional to its momentum, which is called as P. So lambda wavelength is inversely proportional to P, and if we remove this proportionality symbol, we are introducing a constant, and that is H. That H is the Planck's constant. And we all know that. Okay. Yes, Hashira, this is the previous slide. Take down. So let me know once you are done with it, okay? Completed? Okay. Fine. So here the de Broglie equation, it is H lambda is equal to H by P. Okay. So lambda is equal to H by P, where P is equal to mass into velocity. And it is denoted by P is equal to M into V. So in place of P, we can substitute M into V. Okay. So it is lambda is equal to H by mv. So it is clear. This is very, very important. This is the de Broglie equation. This is the de Broglie equation. Am I not audible? I'm not audible to only you guys or for all? What about the others? Hashira, Aisha, am I audible to you? Yes. Okay. Then what happened to the people who are sitting behind 32 batch ID? Okay, I think there is some issue with you guys. Okay, just check it. But no issues. Okay. I will repeat. No issues. The same de Broglie equation you are asking me, right? Want me to repeat the de Broglie equation only? No? Yes. Yeah, de Broglie equation, according to the scientist de Broglie, wavelength is inversely proportional to momentum. Wavelength is inversely proportional to momentum. If the wavelength is very less, then the momentum is more. Okay, that is a relation. If I remove this proportionality symbol, I have to introduce one constant, right? That constant is h. And that h is the Planck's constant, we all know. And also we know momentum is equal to mass into velocity. So in place of p, we can substitute m into v. Okay, lambda is equal to h by mv. So this is the relation we are getting. Is it okay now? So this formula is very, very important. It is clear from the above equation that the value of lambda decreases on increasing either the mass or velocity or both. Because lambda is also inversely proportional to this mass and velocity, right? So if the mass is very less or if the velocity is very less, students, can you hear me and see me now? Sorry for the interruption. Really sorry for it. Some issue with the technical issue. Okay. So what I was telling. So for microscopic objects like electron, the mass of the electron is very less, right? So thank you so much for your understanding, my dear. And um, yeah, for electron, the mass is very less, so the wavelength will be very high. Okay, for macroscopic objects, mass is very high, so the wavelength is very less. Got it? So this is the relation you need to keep in mind. So this is about the de Broglie equation. So from de Broglie equation, you have to study this formula and you have to understand the concept behind it. Got it? Then the next concept is Heisenberg's uncertainty principle. This is one very important principle. So what does this principle says? It is impossible to determine simultaneously the position and the exact momentum of an electron. Momentum is equal to mass and velocity, right? We can keep the velocity because mass will be fixed, only the velocity changes, no? So if you are taking any object, okay, like electron, if you're taking any microscopic things like electron, it is highly impossible to measure both the position of that electron and the velocity of that electron simultaneously. So that is Heisenberg's uncertainty principle. So position is denoted by the letter X and the momentum is denoted by the letter P. Okay, so del X into del P is greater than or equal to h by 4 pi. So this is the mathematical relation we are deriving from Heisenberg's uncertainty principle. Okay, so change in momentum delta x and change in position delta x and change in momentum, that is delta p, that will be greater than or equal to h by 4 pi. So in place of this delta p, we are substituting mass into velocity. Okay, and if you bring this mass to the other side, it goes to the denominator and we will arrive at this particular formula. Okay, so this is also an important formula which is getting derived from the first formula. So it is based on the question. In the question, if mass is given and velocity is given, you have to use the second formula. And if momentum is given in the question, you can straight away use this formula and get the answer. Got it? Delta x is the uncertainty in position and delta p is the uncertainty in momentum of the microscopic particle. Got it? So this is the Heisenberg's uncertainty principle. So just to study the definition and the relation. So the relations are very important. Mathematical formulas, they are very important to solve all the numerical part of this thing. Okay. Okay. So I think this is enough for today. So we will continue with the remaining thing in the next class. Okay. So there were a lot of disturbances and we will continue the remaining part of the next class. Thank you so much for listening to today's lecture patient. Okay. Thank you, students. Bye-bye. Thank you.